Good afternoon, students. Today we are going to see about the audio power amplifier. Okay, so the audio power amplifier, as the name implies, it is a kind of a power amplifier. So in general, what you'll call as an amplifier is the one that is used to raise the signal strength. So you used to have the classifications that depends upon the output voltage requirement. So if you have considered the IC741, so the output power, it can supply the power in the range of 310 to 670 milliwatt. Okay, so this is not suitable when you have gone for the higher current application. So example, an audio application, a typical audio application, it requires the higher currents. Okay, so this can't be delivered by your op-amp. So you are in need of some specialized monolithic ICs that can amplify the audio signals. So that is the thing we are going to see today. And also you might have heard about the power transistors. So instead of using the normal transistors, you can make use of the power transistors. So this will be utilized in the applications where the higher current is required. Okay, so as you know, an audio amplifier is the one that is used to amplify the audio signals. Okay, so as we have seen in the very first class, the loading effect, in order to avoid your loading effect, your input impedance has to be higher and your output impedance has to be lower. So this in turn will be satisfied by this audio power amplifier. So you are having the categorization as low power audio amplifier, medium power audio amplifier and higher power audio amplifier. So whose output voltage is given over here. And also you know that in the case of your power amplifiers, we used to have the categorization that depends upon the operating point. Okay, so that is depending upon your Q point on the load line, we used to have the categorization on the power amplifiers as either a class A amplifier or a class B amplifiers or a class AB amplifiers. So if you have seen in the case of a class A power amplifier, so your Q point, it is biased in the active region of the portion. Okay, however in the case of your class B, it is biased at near the cutoff. So however, if you have compared the efficiency of class A and the class B, okay, class B is having the higher efficiency than the class A operations, and here the output stage, it used to have the push-pull arrangement, contrasting to your class A power amplifier. Okay, so that's the reason in the case of your class AB amplifiers, your transistors, they are biased slightly into the active region. So the reason is that if you have seen the class A power amplifier, as it is acting in the active region, so the 360 degree, the entire input signal in turn will be amplified. However, in the case of your class B power amplifier, as it is near the cutoff, it can have the conduction only for a 180 degree, that is your half of your input signal. So the you might have the advantages combined from your class A as well as in the class B in your class AB amplifier. So that's what it is given here. So if you are biasing the transistors in such a way that it is acting into the active region, and at that same time you can have the conduction that is more than 180 degree, so that kind of amplifiers are notated as a class AB amplifiers. So this is a simple arrangement that depicts the class AB configuration. This is your push-pull output stage. This Q1 and the Q2 that satisfies the NPN and your PNP configuration. So this we used to call that as a push-pull stage. Okay. So this is your push-pull configuration output stage, and which in turn will be derived by your Q3. So this is the point. So to the base you are supplying the input voltage, and you are having the active load, which is your current source, and the drive of your Q1 and the Q3, which in turn will be controlled by this two diodes. Okay, so this is the push-pull output stage, which can also be visualized as a Darlington output stage. So here you are having the NPN pad itself. So Q1A and Q1B, that forms your NPN Darlington emitter follower pad, and Q2A, Q2B and your Q2C. So that forms your PNP configurations. Okay. So the same thing can also be visualized with the help of your Darlington pack configurations. So this is what explained in the case of your single supply audio power amplifier. So if you have seen, again you are having the Darlington pair connection, which is offered by your Q7, Q8, Q9, Q10 and the Q11, and you are having the three diodes, no? So between your two that is your complementary outputs, NPN and the PNP configuration. So these three diodes are there. That is the one that drives your complementary pair. So that diode is there, and a current source will be there, so which in turn is realized with the help of your transistors, and an input stage is also given as a differential pair with a active loads. Okay, so that's what it is in the case of your audio power amplifier. So what we have seen earlier, so here the purpose is that to do the amplification for an audio signals. However, the configuration, you have to keep in mind that the configuration comprises of an input stage, an active load and a combination of diodes to drive your output stage. And the output stage, either it can be a push-pull configuration or a Darlington pack configuration. So in the case of your single supply audio power amplifier, you are having the Darlington pair connection. Okay, and also your output is fed back via the combination of R6 and R7 to drive your Q3. So the purpose of R6 and R7 is to drive the base of your Q3. Okay, and also the R1, it is an emitter follower configuration. So R1 is the one that decides the amount current that is flowing into this particular stage, and again your VCC, it is provided into the Q1 via the potential divider combination of your R2 and the R3. Okay, so that's what it is given here. Okay, so this is the arrangement of a single supply audio power amplifier. So the monolithic audio power amplifier is nothing but your LM380. So LM380, the features of LM380 is listed out here. Okay, you just go through, and it is a 14-pin DIP package. So you are having the first terminal, which is notated as bypass, and the non-inverting input, 3, 4, 5 ground, and the 6th is the pin through which you will be providing the inverting input. 7th again is your ground, 12, 11, 10 are ground, it is not connected. The 9th and 13th, and 8th is the pin through which you will be obtaining the output, and 14th is the pin through which you will be giving the supply. Okay, and another arrangement is also available, which is an 8-pin package. Okay, so that's what it is given here. Okay, so the pin diagram and the symbolic representation. Okay, so if you have seen, so the main components, the 4 stages, as I told you, an PNP emitter follower, a differential amplifier, a common emitter amplifier, and the quasi complementary emitter follower. So these are all the 4 main stages involved in the LM380, which is available as a monolithic audio power amplifier. Okay. So this is the arrangement of your audio power amplifier. So if you have seen, so here you are having the first stage, which is formed by this Q1 and the Q2. Okay, so which is then a PNP emitter follower input stage. So in that its output drives your Q3 to Q4 combination. Okay, so if you have seen, so this is a differential pair arrangement. So one of your Q1, it accepts the inverting input, and another one it accepts the non-inverting input. Okay,